Hello everyone. Today we're going to be talking about a paper called Incentive Mechanism Design for Unbiased Federated Learning with Randomized Client Participation. First, let's take a look at the background. Basically, federated learning trains a shared machine learning model across different clients in a distributed manner without having to share each client's local data. However, clients may choose not to participate in training the model because of the cost they might incur. So here in this case, the server is gonna need to incentivize the clients to participate by giving them money or services or something like that in order to ensure high quality training. However, the incentive mechanisms that are present today have flaws. In this figure, you can see how federated learning works. Now let's talk about the contribution of the paper. So first, the authors introduced two new concepts. Intrinsic value, which is how motivated the client is to training the machine learning model without monetary payment, and also bidirectional payment, which basically means that the client can pay the server and the server can pay the client. So using these two concepts, the authors propose unbiased incentive mechanism with randomized client participation. So this proposed mechanism customizes payments based on each client's participation level and intrinsic value, and also allows bidirectional payments.
Oh, hello everyone. Next, we will go to the problem settings. To achieve this goal, the authors introduce the price vector P and the participation level Q for each client. In order to transform the problems into a tractable form, they first conduct the convergence analysis and they build the upper bound for the expected loss. Next, for the cluster problems, by utilizing this upper bound, the cleanse problem becomes concave and the P can be expressed in terms of Q. And for server's problems, it is transformed into a convex optimization problems which can be solved by the software. And then server build several equations to demonstrate the relationship between P, Q, and many other quantities like intrinsic values. And the final takeaways in theoretical part is for the server's price, it should be correlated with client's participation level, and the incentive payments are bidirectional. From the server's perspective, the server should set higher prices for clients who have larger local costs, and the clients should participate to ensure the model convergence. But from client's perspective, clients with higher intrinsic value should not participate in model training.
So in the experimental evaluation, the authors deployed the incentive mechanism on a real-world federated learning setup consisting of 40 Raspberry Pi clients and a central server. Each client was allowed to decide the participation level based on their own incentive offered and simulating a realistic cross-device scenario. So the setup tests the model on three data sets, which is the synthetic data set, the MNIST data set, and the EMNIST data set, each reflecting different system characteristics. For instance, the EMNIS setup had a low local cost and a high intrinsic value, encouraging the voluntary participation. In contrast, the EMNIS setup modeled the high cost clients who required greater incentives to remain engaged. So the results shown in the table in the center highlight both speed and utility gains for MNIST. The proposed pricing scheme reached 89%, the accuracy in just 411 seconds, over four times faster than the uniform pricing. Even in the more challenging EMNIST scenario, the accuracy improved at twice the speed compared to the baseline. Moreover, the total client utility increased dramatically across all setups, with gains exceeding 77,000 and 86,000 utility units in MNIST and EMNIST, respectively. So these outcomes validate the effectiveness of the proposed mechanism, not only in accelerating the model convergence, but also in ensuring that the clients are compensated fairly and participate proportionally to their value and cost. Thank you.